All right, let's dig into the world right under our feet. We're going to uncover an invisible universe, a microscopic city that, believe it or not, holds the key to almost all life on land. It's a wild story about a locked pantry, some secret chefs, and an incredible journey that makes everything grow.
So let's start with a puzzle. It's something that happens in every single garden, farm, and forest out there. You have plants, and they're literally sitting in a buffet of food, surrounded by nutrients. So why can't they eat it?
Well, because, and get this, a staggering 98% of the nitrogen in the soil is locked away, and nitrogen is one of the most important things for a plant to grow. But it's in an organic form they just can't use. Their roots can't absorb it. It's completely off limits.
Yeah, you can think of it just like this. The soil is a giant pantry, totally stocked with all the goodies a plant could ever dream of. This pantry has a name. It's called soil organic matter, or SOM for short. But for the plants, well, that pantry door is locked up tight.
Okay, so let's take a closer look inside this pantry and figure out what's really going on in there. What you've got to understand is that soil organic matter is basically the collected treasure of the soil. It's all the old decaying plants and animals built up over time. It's this huge stockpile of nitrogen, phosphorus, and sulfur. But here's the key. It's a stockpile, not a restaurant. Plants can't just stroll in and grab what they need. So, if the plants can't get into the pantry, who can? Well, this is where our story gets really, really interesting. It's time to meet the trillions, and I mean trillions, of invisible heroes working 24/7 right under the surface. These are the soil's secret chefs. We're talking about an invisible army of bacteria, fungi, and other microbes. They're the only ones who have the key to that pantry. And their entire job is to break down all that complex stuff in the soil organic matter and basically cook it into a meal that plants can actually eat.
And there's a name for this whole microscopic cooking process. It's called mineralization. It's like biochemical magic. It's the moment they turn these big, complex organic compounds into simple inorganic molecules. And that is the only form of nutrients that plant roots can soak up. Without mineralization, that pantry stays locked. Period.
Now, this is where it gets really cool. To see how it works, we're going to follow a single nitrogen atom on its incredible journey from being a locked-up ingredient to becoming a 5-star meal for a plant.
This whole conversion basically happens in 3 main stages, kind of like a culinary assembly line. We start with ammonification, then move to amodification, and we finish with nitrification. And each step is handled by a totally different specialized crew of microbial chefs. All right, first up, amenization. You can think of this as the prep work in the kitchen. Specific bacteria, like Pseudomonas and bacilli, they're the first-line chefs. Their job is to chop up the big, tough proteins from the organic matter into smaller, more manageable bits, like amino acids and urea.
Then for step 2, a whole new group of specialists takes over. They perform what's called ammonification, turning those amino acids into ammonium. And this right here is a huge deal because ammonium is the very first form of nitrogen that a plant's roots can actually absorb. The first course is officially served.
And this diagram just shows that critical handover perfectly. You got the complex organic stuff on one side, all the dead leaves and proteins, and on the other side you've got the plant ready to eat. Ammonification is that vital bridge right in the middle, turning complex waste into the first available nutrient, ammonium. But hold on, the kitchen is not done yet. There's a final team of gourmet chefs, and they step in to refine the meal even further. This is a 2-step process called nitrification. First, bacteria called Nitrosomonas, then Nitrobacter, convert that ammonium into nitrate. And nitrate is another nutrient for plants that's even easier for them to absorb. Now, the full menu is ready. But here's the twist. This kitchen isn't just a soup kitchen, okay? It's not a one-way street. These microbes, they have needs of their own, and that creates this fascinating, this give and take in the soil. So for every action, there's a reaction, right? While mineralization is releasing nutrients for the plants, there's a competing process called immobilization that's locking them up again. Why? Simple. The microbes need nitrogen to live and grow too, so they end up eating the very nutrients they just cooked up, creating this constant tug-of-war in the soil. So what decides who wins this tug-of-war? It all comes down to the microbes' diet, specifically the ratio of carbon to nitrogen in whatever they're eating. If there's a ton of carbon compared to nitrogen, like in something woody, the microbes get super hungry for nitrogen and just hoard it all for themselves. That's immobilization. It's actually why, if you mix a bunch of wood chips into your garden, it can sometimes stunt your plants for a little while. The microbes are eating all the nitrogen first.
So you've got this constant push and pull. This is the central drama of the soil's nitrogen budget. Nitrogen is always being added, changed, and, let's be honest, sometimes lost. It can escape back into the air as a gas or just get washed away by water. It is a crazy dynamic system.
Now you're probably thinking, how on earth can anyone even begin to predict this? But for gardeners and farmers, this is a huge deal. And they can actually get a pretty decent estimate of how much nitrogen their microbial chefs are going to serve up each year. They use a rule of thumb, calculating based on the percentage of organic matter, the soil's weight, how much nitrogen is in it, and an estimated mineralization rate, which is usually somewhere around 2 to 3% per year. And it's just mind-blowing when you think about it. This whole planet-sustaining process really just boils down to the biochemistry happening inside trillions upon trillions of individual bacteria, like this one. Each one is a tiny, powerful little engine driving the entire cycle of life. So, at the end of the day, what does this all mean? The big takeaway is that this microscopic journey from a complex protein in a dead leaf all the way to a simple nitrate molecule getting soaked up by a plant root is what keeps our soils productive. It's the fundamental process that feeds us and keeps our whole environment in balance. It really makes you look at the ground differently, doesn't it? It leaves you with one last thing to chew on. Is the ground we walk on just, dirt? Or is it one of the most complex, bustling cities on the planet, working around the clock to feed the entire world? Pretty amazing stuff. Thanks for tuning in.